Okay, testing, testing. I think we should be okay. But today I'm on a different setup, so bear with me. The audio quality is probably going to be a little bit worse than usual. I'm just away from home. Okay, so we're going to start with the problems. I think the very first problem is asking about whether two lines are parallel. And if the lines are given by 4t minus 3, 2t plus 6, and 3t, you have 3t, and 3t plus 4. It's terrible. Minus 2t plus 7. So if this is the first line and this is the second line, right, this corresponds to a vector of 4, 2, and 3, just reading that off the coefficients, right? The constants are just sort of where the constants are just sort of displacements, right? Like, as opposed to a vector going directly through the origin, opposed to a vector going through the origin, now it's vector going through some points, what, -3, 6, and 0. But all that matters for the question of parallel or orthogonal is going to be the vector itself. You don't really care about the position. That's why we only look at the coefficients in front of the t's. So likewise, this becomes 3, -3, and -2. Again, just looking at coefficients. So then the idea is you take this, and you take the dot product together, and if I remember correctly, you should end up with 0. Yeah, you should end up with 0. So it's going to be perpendicular, right? And I don't know. I don't think there's too much value for me doing out the nitty-gritty math, but dot them together and you should see you get 0. And remember, when you... Actually, let me maybe draw a little diagram for you. Just as a quick reminder, um, for testing whether lines are parallel or perpendicular, two lines are perpendicular when A dot B, right, when vector A and vector B are perpendicular when they're... So I guess two vectors perpendicular when their dot product is 0 or their cross product is maximal. Yep. And similarly, they're parallel when A dot B is maximal, whereas the cross product is 0. So keeping this train of thought for the next part, we see that we have some function ft minus 3, 2t plus 6, and 3t. And we're being asked to compare that to the plane x plus 4y minus 4z is equal to 2. And of course, when we have problems trying to ask about whether a line is parallel or perpendicular to a plane, well, first of all, this line just becomes 4, 2, and I guess positive 3. For the same reason as before, we only need to care about the coefficients in front of the t. And this one right here becomes the normal vector 1, 4, and -4. Should recall, you can get the normal vector just from the coefficients in front of each of the variables. So what this looks like is if you have x, y, and z, and you have some plane that looks like this, right? The normal vector the normal vector is normal to the plane, and you have some other vector, um, you have some other vector. Let's maybe call this thing just v. So the idea is, um, yeah, let's say v goes like this. If v is inside the plane, then it's going to be perpendicular to the normal vector. Likewise, if v is perpendicular to the plane, it's going to be parallel to the normal vector. You got that? So the normal vector sort of captures all the information about the plane, but kind of opposite, so to speak. So let's just go ahead and test v dot n and see what happens. And I think you'll find that when you dot those things together, what do you get? 4, 8, -12, you get a 0, right? So when the normal vector and the vector in question v are the dot product 0, so they are perpendicular, that means that v and the plane are parallel. or rather v is parallel to the plane. Yeah, my wording here is a bit wonky, but hopefully you get the idea. Um, right. So now, okay, what next? Okay, so then the next one is about two planes, and we're trying to figure out what the relationship is. So this is x plus 4y minus 4z is equal to 2, and 3x minus 12y plus 12z is equal to 4. And as before, let's just get the normal vectors. So the normal vector for this one is just 1, 4, and negative 4. Just reading off the coefficients again. And for the other plane, it's just 3, negative 12, and 12, right? So what we notice is that one of these is a multiple of the other. Again, the part over here doesn't really matter. It's just telling you how much the plane is shifted up or down, or in whatever direction. But what we can see here is that the normal vectors are one has a multiple of the other. So that should be our hint right away that the two are parallel to each other. But if you really wanted to do it, you could take the cross product of each other, right? So you could take the cross product n1 cross n2 and verify that that's equal to 0. Or, as before, you could verify that n1 dotted with n2 has absolute value of n1 times n2, right? So either of these will let you verify that the normal vectors are parallel to each other, which means that um, the two planes have to be parallel to each other. Uh, oh, sorry, did I get my signs wrong here? There should have been a negative sign right here. There should be a negative sign. Yeah, but visually what this means is if you have one plane, right, its normal vector looks something like that, and the other plane, is maybe below it, and its normal vector looks like, 3 times as large, but in the same direction, well, that means that the two planes are parallel, right? If their normal vectors are parallel to each other, the planes have to be as well. Again, this is sort of the intuition that the normal vector contains all the information about the plane, other than it's like how far shifted it is. The normal vector contains all the information about the plane's orientation, let's say. Anyways, let's keep going. This next one's a little bit weird, but if you have 2 points, 3, negative 2, and a, b is equal to u comma v comma 6. The deal here is that, okay, if you want to say that they have two planes lie in the same, the line between them is parallel to the y-axis, right? So if this is x, this is y, and this is z, and this is point b, and this is point a, I guess. What this is saying is that uh, their x and z components are exactly the same, but that their y components can differ by anything. Right, their y components being the negative 2 and the v. So what this is saying is that 3 has got to be equal to u, a has got to be equal to 6, but then negative 2 is equal to v plus t for any value t, or just uh, how else do you want to write this? Or v is equal to anything, or just don't write it at all. Don't write it at all and just leave it as this. Now, if you want to express it as a single like equation, maybe the way to do it is saying that 3, negative 2 comma a is equal to u v plus t 6. So a couple different ways, but the point is the x and the z have got to be fixed because if it's parallel to the y component, that means the x and the z, sorry, if the line is parallel to the y component, that means that every point of the line has to have the same x and z values. It's just that the y is allowed to shift. And that's what we're representing by the t, the parameter t. Or again, you could just say v is equal to anything, or you could just, not even write that at all and just leave it as this. 3 is equal to u and a is equal to 6. But continuing onwards, now if we want to express that they're in the same plane, now it's sort of like saying that um, what is it? U comma v comma 6. Now it's kind of saying that the y value has got to be fixed, whereas the x and the z can be anything, right? So if this is b and a is 3, negative 2, and a, little a, this is saying that v and negative 2 have got to be equal to each other, and there's no other information about the little u or the little a. So v is equal to -2 is all we can say, or is all we need to say, right? It's basically just saying that, it's basically just saying that the plane is inside, excuse me, the plane is defined by y is equal to -2. So similarly, because v is the y component, it's got to be equal to -2. I think that's all there is to say about that one. Okay, onwards. We're gonna just say that if one point is the center of the sphere and one point is the center of the sphere and the other point is uh, on the surface of the sphere, right? That's basically just like saying, okay, what do we want to say here? Um, B is on the sphere centered at A. Well, okay, I'll just write this out a little bit thoroughly. So if A is here, right, and B is somewhere out here, well, first ignore B and just write the equation of the sphere centered at A with that radius, which is just, I think, x minus 3 squared plus y minus, or I guess y plus 2 squared plus um, z minus a squared is equal to 5 squared, right? So the radius is 5. And now all you have to do is just plug in u for x, v for y, and 6 for z, and that's all you have to do, right? Let's just plug in the points of B into the x, y, z. Yeah, that's all there is to say. And then for the last one, you're being asked to say that B is on the paraboloid defined by z is equal to x squared plus y squared. And it's a very similar idea, right? Whatever points you had for what was B equal to, u, v, and -6, right? Just plug those in and you should be golden. Or u, v, and +6, I guess, whatever. But yeah, that's the point. Just this was like you're not asked to do much, right? They give you the equation of the paraboloid and you're just asked to plug it in. The fact that B is on that surface means that it satisfies the equation. Okay, so we're making good progress. Some of the early problems are not so bad, but the later one is so obnoxious. But you're being told that some ball has like um, acceleration of -12 feet per second squared on Mars, right? And I think we're using the coordinate axis where upwards is the positive j hat direction and rightwards is positive I hat. But I don't even know why you care about I for this problem. There's no horizontal motion, it's all vertical, but whatever. So part A is asking you to figure out what V is, right? So maybe let's call this A of t, as a function of time. It just so happens that there's no dependency um, because the acceleration is constant. So this means that V of t, I guess we should just be careful and draw arrows over them, is equal to we're just integrating, minus 12. Okay, so that's plus 0 I hat, right? So this turns into v of t is equal to minus, you integrate this, right? So this becomes 6t j hat plus, excuse me, minus 6t plus c j hat. Again, I hat is 0. I'm not even going to bother with a constant, right? But for j hat, you have to think a little bit about what the constant of integration is. But because we know v at the start is 0 because we're told that it's at rest, that means c is equal to 0. So all that you're left with is like minus 6t. Excuse me, I'm an idiot. No, what am I doing? What am I doing? It should be minus 12t. What am I doing? Yeah, I got it confused with the next part. So the integral of minus 12 is just minus 12t, right? That was just a computation error, silly me. So the next part is asking you about the position vector. And you just integrate that again, so that turns into minus 6t squared plus c j hat, right? And now we know that position at 0 is equal to 24. Okay. Or I guess 24 j hat. So when you plug in 0, you get that c is equal to 24. You just take this thing, plug in 0, and you get that c has got to be equal to 24. So let's write that down, 24. And I guess I hat is again 0. Now it's asking you to figure out when it touches the ground. So just solve for minus 6t squared plus 24 is equal to 0. You get t is equal to 2, I think. And now it's asking you the speed, right? So now the speed is just absolute value of v of 2, speed when it touches the ground. And you end up getting like 12 times 2, absolute value of 12 times 2. Yeah, I'm just basically plugging it into this equation right here. And that gives you, what, 24? Okay, very good. So, okay, onwards and onwards. Okay, I hope I'm still recording. Seems good. Audio check. 1, 2, 3, 1, 2, 3. Yeah, let's cruise through the rest of this. Like later problems are super obnoxious, to be quite honest. But it's not that bad yet. Okay, so the next one looks like this weird contour plot. I wish I could just maybe draw it. Okay, no, I can't. So what is it asking you to do? It's asking whether fx and fy are positive, negative, or 0 at p at q. Well, let's just look at the diagram, right? So what is it at p? Fx is just the partial derivative in towards the, we're assuming it's the right direction, is by convention. Yeah? So what this is saying is, if it's at height 25 here, and at height 20 here, and at height 15 there, like when you go rightwards by like a step, it means you're going downwards, right? Because you're at 20 here and 15 over there. You take a step, like a small step, you're going downwards. So fx is negative. Similarly, just going upwards, right? Fy is in the upwards direction. Going from P a little bit upwards, hopefully you can see this well, you're going from 20 towards, lower elevation, so that's negative as well. And yeah, that's all there is to that one. Now, the second partial derivatives are kind of nasty. And the way to visualize this is sort of saying, although, how did they express it? So this is the area in question as a contour plot, right? And that's kind of a hill. And you notice that it's sort of scrunching up in a certain way where um, it gets more steep out here and is not as steep over here because the spacing is larger. The point that I'm trying to make is that if we try to visualize this instead as like a 3D hill, right? So if this is point like P, and this is like a 3D hill where P is like, I don't know, back there somewhere. The idea is we're trying to find like basically trying to find the concavity of our path that we travel if we just walk like in this direction or this direction. And you can kind of see that, right? So this direction is probably easier to visualize. But if we're sort of like going across like that way as the bird flies, that means we're kind of like walking along the hill on like some kind of curve. We're not quite touching the peak. We're kind of like shifted over a little bit from the peak, right? But you can kind of see that this shape is more or less, concave down, which is our clue that if y is less than 0. And just by symmetry, the exact same argument applies for fxx, because it's like more or less a circular hill or like a dome. But like that would just be sort of like walking. It's so hard to draw this into the page, but it's kind of like, it's kind of like going, we're kind of like starting down below and starting south and walking north, right? That's kind of this path right here. But it's sort of like saying, okay, we would be going like here, then we would be sort of dipping back down, right? And that's sort of like, that path sort of is concave down. And that's what f of x is also less than 0. Now, as for the mixed partials, that's even harder to visualize, and this problem is kind of nasty. I don't know why they're asking you to visualize the mixed partials. I feel like it's a silly exercise. But you can kind of see like, okay, so this matters because this actually matters how scrunched up the lines are. But you can basically, I wish I could just draw on this thing. But the idea is each of the partial, it's basically saying, okay, let me try to draw this. Okay, so understand that it sort of gets scrunched as you go downwards, right? It's more sparse up here, but more scrunched over there. The idea is basically just look at each of the partials, right? It's basically don't, as you go upwards, consider taking a right step at each point, right? That's sort of what it means by the partial of x, the partial of x and then partial of y means that you sort of look at each of the partial x partials as you march along in the y direction, right? And what this is saying is, okay, for each step that you consider taking, is it more steep up here or is it more steep over here, right? Is like more steep a little bit north of P or a little more steep a little bit south of P? That's what that's asking. And now you kind of have to visualize, you kind of have to look a little closely, but over here, it's not as steep, right? Over here, the lines are a bit more sparse, whereas up here, the lines are more scrunched. So what this is saying is that as you go upwards, each of your rightward steps become more steep in the in the downwards direction, right? So that's why it's, I think, less than 0. This one's hard to visualize, right? If this is too hard to visualize, maybe just take the loss for it. But over here, it's more steep downwards. Up here, it's less steep in the downwards direction, right? So hopefully that makes some sense. That's what f of x, y is, right? It's saying all the partials with respect to x, and then just think about how those change as you march along in the y direction. Um, yeah, right? Because, like, how do you put it? Each of your steps are in the negative direction, but it's getting more and more negative, which means that your sort of like fxy is negative. Okay, hopefully that makes some sense. That one's kind of hard to see. Don't worry too much if you don't understand the mixed partials. What else is there to say about this one? I think they were asking about the critical points, right? Yeah. So the critical points. Um, okay, so I'm going to draw like something like that, right? So obviously, like this one's kind of sticks out, and this one over here is also kind of, well, should hopefully stick out. But this one right here is just the top of the hill, right? Or is it the bottom or the top? I think it's the top. You just have to look at whatever the values are. But that point over there, I think, should be the max. Whereas the point of over here, right, you can kind of see it's neither a max or a min, so that should be a clue right there by process of elimination. But if you want to argue a little bit more closely, you can kind of see that it's, the change in the level curve is 0 in these 4 directions, but is non-zero in these, which means it's a saddle point, right? It's a saddle point. Um, yeah. So that's those two. Um, so now it's just being asked to sketch the gradient. Okay, so they saved the easiest one for last. Well, recall that the gradient is just going to be perpendicular to the level curve, right? It's the direction of greatest increase. So it's got to be orthogonal to the direction of no increase. So just getting rid of these lines for a second. Right. So it's either going to be in this direction or this direction. And whichever one it is, you just got to choose the direction of positive increase, which I think is towards the top of the hill. Yeah, so it's gonna be this one. Okay, so we're making okay progress. The last two are super nasty. Like honestly, just I feel like they're terrible questions. Okay, so we're considering some function f of x y is equal to 2x cubed plus 3x squared plus um, y squared minus 12y. And we're considering this on some domain from 0 is less than or equal to x, less than or equal to 2, and 0 is less than or equal to y, less than or equal to 10. So these problems, let's break it down a little bit, right? It's sort of saying this is the x-axis, this is the y-axis, this is 0, this is 2, this is 10, and it's basically saying, okay, find the smallest and largest values in here. So let me break it down. Multivariable calculus um, is going to be able to find the critical points agnostic of the boundary, right? So, which means that after we do use multivariable calculus and set the partial is equal to 0, we still have to go in and check the boundaries themselves because, um, because so to speak, the calculus doesn't understand that there's a boundary, right? In single variable calculus, right, it would have situations where, let's say you had a parabola, right? But you were limited to, let's say, here and here. You were limited to this region, right? In which case, your minimum you could find from, doing a critical point with calculus, but your maximums, aren't some like inherent property of the function. Your maximums are just sort of exist because you set those arbitrary boundaries. And calculus is not so good for catching that, right? So the idea, or sometimes it does just by coincidence, right? If you had a situation where, your boundary was like right here and like right here, then yeah, it turns out that calculus does catch, it does find the critical points that just happen to be your boundary, but that's a coincidence. But in general, you kind of have to use calculus to check for critical points, and plug those values back in and figure out what those are. And then you also have to check on the boundary. But whereas single variable calculus checking the boundary is easy, in multivariable calculus it's kind of hard because this means that you actually have to do like 4 individual functions representing, the 2D function constricted to this line, the 2D function constricted to this line, and so on and so forth for each of those boundary lines. We'll talk about that more in a second. But then at the very end, you also have to check the corners, right? The actual vertices. So let's maybe split this up into 3 parts, right? So use multivariable calculus to find the, I'll call them multivariable crit points, right? So then this is step 1. Then step 2 is use single variable calculus to find the single variable critical points, right? That means the critical points along each one of these lines. Because the idea is if all that if all you know about the function is that it's sort of going along this one line, restricted to this one like single dimensional domain, then you know that then you can actually find the critical points using single variable calculus because it's a single variable, a single dimensional space. Um, this might be a little bit uncomfortable, but bear with me. But then at the very end, just test all the vertices too. Test all the vertices too. Okay, so for part 1, we basically do this by saying, okay, f of x is equal to 0 and f of y is equal to 0. And then figure out what those are. I think, okay, so f of x is basically 2. What does it turn into? It turns into like 6x squared plus 6x. And you set that equal to 0, so x is either equal to 0 or negative 1. But negative 1 is not in our domain, so ignore it. And y is equal to anything. Okay, so then fy is equal to 2y minus 12, and you set that equal to 0, so y has got to be equal to 6, and x is equal to anything. Okay, so then when fx and fy are simultaneously equal to 0, then the constraints just become x is equal to 0, y is equal to 6. So this is our only crit point that's inside the region. And if we plug in f of 0 comma 6, I think we get, just plug it into the original expression here, I think we get just negative 36. And as it turns out, that happens to be our minimum, but we don't know that yet because we've got to check everything. So now this is where the problem just turns into a giant pain in the butt, right? At this point, you need to, so now we've done step 1. We've used multivariable calculus to find the multivariable critical point, so to speak. By the way, this terminology is sort of my own, but I hope it's reasonably intuitive, right? It's saying, when you treat this as a surface or, when you consider all the dimensions, think about what the critical points are. But now we need to sort of go along each one of these lines and figure out, now we need to restrict the function to be like 4 one-dimensional functions and figure out what the crits are along each of those lines, right? And let me sort of explain why you need to do this, right? Because like if you had something that looks like a saddle point, right? In multivariable calculus we've talked so much about how a saddle point is not a critical point, right? At least when you consider all dimensions. But like let's say you're sort of just marching along like the x-axis, right? So like how do you put it? This saddle is sort of like saying, yeah. So this part right here is sort of like in the plane of the page, whereas the other part is sort of like going into the page, right? Sorry, it's hard to draw a saddle, but I hope you get the idea. So the idea is that let's say that you're Stanley, right? You're like a lower dimensional person, and you're just sort of like walking along in the like x direction, okay? So you're basically just walking along this hill, and you have no conception of this stuff around, right? You can't see to your left or right. You can only walk forwards. Well, if you only walk in like one direction, well, suddenly this point does look like a minimum to you, right? If you can only walk in one direction, which is sort of the idea of like confining yourself to one of these lines, right? A single dimensional path, right? You have no idea what any of this crap is, right? All you see is that, well, hey, I'm at the bottom of a valley right here. This is a minimum. So that's what I mean by like it's sort of a one-dimensional minimum. And this comes into play when you start restricting the domain, right? It's kind of complicated, but sorry, I think this is just something you have to sort of like hopefully grasp. Realistically, this is more complicated than realistically, this is what you need to do for it to be correct, but I think most teachers imposing these kind of problems um, are not gonna choose functions where it turns out the max or min end up here. So if you're rushed for time on an exam, maybe just check 1 and 3. But for like full completeness, you would need to check 2. But okay, let's go so let's basically show you how to do this, right? So the function at this point just becomes, this line is basically f of x with y being fixed to 0. Here it's f of x with y being fixed to, I think, 10. Here it's sorry, this one is f of 0 with y being allowed to vary, and this one is f of 2 with y being allowed to vary. So each of these functions are basically functions of one variable, either x or y, but not both. Right? So at this point, you can basically just do um, your regular single variable calculus. So f of x comma 0 is just equal to 2x cubed plus 3x squared, because the y terms just go away. Right? All I'm doing is taking the original expression, this thing, and plugging in y is equal to 0, and this is what I get left with, 2x cubed plus 3x squared. So at this point, I don't know, do you want to call this just like g1 of x maybe to stop thinking about f? But then g1 of x, we're trying to find the critical points. That's when 6x squared plus 3x is equal to 0, and this happens when x is equal to 6x 0 or -1. And again, -1 is not in the domain, but x is equal to 0 is. So then when sorry, I'm just trying to double check my notes here. X comma 0. Yeah, this one's kind of lame and not very illustrative. Yeah, so this means that this one's not saying a ton. It's basically just saying, okay, from the perspective of walking along this line, right, the single variable crit point is like right here, which we were going to check that later when we are going to test vertices anyways, but sure, let's go ahead and do that now. So f of 0 comma 0 is just 0, right? We're just plugging that in here, where g1 of 0 is equal to f of 0 is equal to 0. Okay, so maybe this is, maybe this is a maximum. We're not sure yet. All we've seen so far is a -36, but let's keep going, right? All this is saying is that the only crit point, single variable critical point along this line is at x is equal to 0, and that value gives you 0. So now we just keep going, right? g2 of x is equal to f of, let's say, x, comma, but I'm defining g2 of x because I'm hoping it'll be more clear, but hopefully it's nice. So now f of x comma 10 is equal to, I guess it's like 2x cubed plus 3x squared minus 20. So again, we sort of do the exact same derivative. So g2 prime of x is equal to 6x squared plus 6x is equal to 0. But, this is basically exactly because the two equations only differ by a constant, minus 20, which, again, popped out when you plugged in 10 for y. The crit point, is still the same, right? X is equal to 0 or -1, but -1 is not in the domain. So now you just plug in g2 of x g2 of 0 is equal to f of 0 comma 10, which is equal to minus 20. Okay, so you basically just keep doing this for all the, for all the 4 lines. And, I guess just for thoroughness' sake, I will show you. So f of 0 comma y just turns into y squared minus 12y. Then f prime of, maybe I'll call this h1 of x, h1 of y. So then h1 prime of y is equal to 2y minus 12. So then this is critical when y is equal to 6, I think. So then that corresponds to when f of 0 comma 6. And that gets you -36, I think. But this turned out to be the exact same point that we got from our multivariable calculus. This turned out to be the exact same point, 0 comma 6, that we got from our multivariable calculus critical point, right? So this is what I meant earlier by you could have, sometimes, you could have a coincidence where one of the boundary points, uh, one of the extrema on the boundary points turns out to be one of the extrema from multivariable calculus. Hopefully that's not too confusing, right? What I'm saying is this happened to be a a critical point, a minimum, a local minimum in multivariable calculus, but it also happened to be a minimum when you restricted it just along one line. And that should hopefully make sense, right? Like if you've just got like a circular valley, right? This is the point that's a minimum in every, or how do you put it? This is a point that's like a minimum in multivariable calculus. But let's say you like restricted, or how do I put it? Let's say that your domain is just restricted to be like the part that's underneath this like grid, right? So even though this is the minimum that you got from the calculus, it turns out to be a minimum that you can get from the boundary as well. Sorry, this is really hard to draw, but just imagine that like there's like a square boundary underneath here, and this point is above some point on the left boundary. Anyways, that's a bit of a diversion. Let's not get too much into that. But okay, f of 2 comma y is our last one. So this is equal to like y squared minus 12y plus 28, I guess. And okay, then h2 of prime of y is again equal to just 2y minus 12. Is that equal to 0? Y is equal to 6. So then or I guess like f of 2 comma 6 is equal to, I didn't even calculate this one out. What is it? I think it's like -8. Okay, so now we've checked the crit points and plugged them in for each of the 4 lines. And, one of them was redundant because we already saw it, but then the other ones don't seem particularly small or large. -20, 0. Um, yeah, so this is part 1. This is the value we got from doing multivariable critical points. And now this is all the individual lines we get. Like, this problem is such a pain in the ass. I think it's really annoying. But now, okay, so now we need to check the vertices, right? That's the last step. 3 is check the vertices. And I'll just go ahead and let you plug them in yourself, but I think I found that. What did I find? I think we found that f of. Mm, which vertex was it? What did we find? The vertex of. One of them was 28. Which one was it? I forget. Um, 2 comma 0. Yeah, I think it was 2 comma 0. This one right here. When you plug that in, you turns out that it gave you a value of 28. F of 2 comma 0 is equal to 28. And just it turns out that like basically at the end of all this process, you do an intake for every single like vertice value you found, like every single value the function took on at the vertice, at the crit points, at the multivariable crit points, etc. And just consider all of them and just take the minimum and the max. And it turns out that 28 is your largest one and like -36 was your smallest one, right? But if you were being, if you're being thorough, I didn't write them out. You would have to figure out what the function value is at these points as well. So there's that. Yeah, this problem is really nasty, and the next one is even nastier. Like honestly, it sucks. Um, yeah. So the next one is basically saying, okay, same function, but now just figure out what the best, what the optimal values are um, between y is equal to 1 and y is equal to 5 minus x squared. So it's kind of a similar process, but um, the idea here is now 1 is, find the multivariable calculus crit points. Number 2 is find the single variable calculus critical points. And number 3 is, um, find the vertices or check the vertices. So this part 1 is the exact same as the previous part, so I'm not going to do it again, right? It's just setting f of x is equal to 0, fy is equal to 0, and then checking to see if any of those critical points are inside the domain, which I actually don't think they are. I think they actually like land outside, right? I think that it's a point like, sorry, I'm trying to remember. I remember the crit points were like 0 and 6 and -1 and 6, right? That's just from setting the partials equal to 0. So it turns out that these are irrelevant for this problem because it's outside the domain, right? Because the height of 6 is too high. This parabola only goes up to y is equal to 5 at the very tip. So, okay, now we find the single variable calculus, crit points, and now is where things just turn into a pain in the butt. So whereas before we had four really nice straight lines, now we have one nice straight line, but now we have a parabola we need to contend with. So that sucks. So, okay, how do we put it? So this line right here is f of x comma 1, and this line right here is f of x comma 5 minus x squared, right? All I'm doing is plugging in the value of y, replacing it with 5 minus x squared. So, okay, the first one is not too bad, but f of x comma 1 is just equal to 2x cubed plus 3x squared minus 11. Now you take the derivative of this, and this just turns into 6x squared plus 6x is equal to 0, so that, to find the crit point. So now x is equal to 0 or minus 1. Okay, 0 or minus 1. And remember, y is still equal to just 1. So yeah, okay, go in there and check out whether those are, go ahead and plug those in and check what those values are. I don't think they end up being particularly, I just don't think they pan out, right? So let's just check f(0), 1 and f of negative 1 comma 1. What is that? That turns into like, what's the original function? Where did I put it? Yeah, these problems suck. I think this one just turns into like minus 11, and this one turns into like, what does that turn into? Minus 2, 1. I think it turns into like minus 10. Is that right? Anyways, I think it turns out to not be a critical point, so it's don't have to worry too much. But okay, so that was from that was checking along this line right here on the domain, right? Now we have to check the parabola, which is using f of x comma 5 minus x squared, and this sucks a little bit, not too much, but f of x comma 5 minus x squared, right? If you want to, you can think of this as a single variable function, right? G of x, and you can tell because it's just a line, right? A line is a single variable. Um, like you can kind of think of a line as as a single variable, like um, what do you call it? Like a single variable object. So hopefully this isn't too crazy. But this turns into 2x cubed plus 3x squared plus 5 minus x squared minus 12 times 5 minus x squared. Just plugging it all in. Now I'll leave the math to you, but now you need to take the derivative, right? G prime of x is equal to blah, 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 and set that equal to 0. I'll let you do the math yourself, the calculation yourself, but I get that once I reduce this a bit, I get that 2x squared, sorry, 2x cubed plus 3x squared plus 5x is equal to 0. And so this happens when either x is equal to 0 or 2x squared plus 3x plus 5 is equal to 0. Right, so one of our solutions is when x is equal to 0, and the other solution is when the other solution of whatever value of x satisfies this quadratic equation. But as it turns out, if you plug into the quadratic equation, this has no real solution. So this is the only one we need to care about. And what does this correspond to? This basically corresponds to the peak of the parabola right here, when x is equal to 0 and y is equal to 5. And as it turns out, f of 0 comma 5 is equal to, I think, minus 35, which, as it happens, turns out to be our minimum. You don't know that yet, but after you look at all the options, this one does turn out to be the minimum. Okay, that's that. Now what do we need to do? Now the last part, right? So we've done this part, finding all the single variable calculus crit points. And now we just need to check the last two vertices, this thing and this thing. I'll let you plug it in yourself, but I think this one in particular, f of, what is this? F of 2 comma 1 turns out to be positive 17, which is the other maximum, whereas this one turns out to be like f of minus 2 comma 1 turns out to be minus 14, which isn't a maximum or minimum, so we don't care. But yeah, the final question is 17 and minus 35, so yeah, that's what that is. This sucks, right? I think this problem is computationally terrible. I don't know why they would choose to put this in the exam. Anyways, now we're getting to the end. So I think the function we're dealing with here is y is equal to 2x or minus 2x and the parabola, right? The parabola is y is equal to x squared. And the idea is we're trying to figure out what the integral of x minus y is on this area dA. Okay, so the first thing to do, it's asking us to solve this two ways, and to verify that either way will give you the same answer. I'll walk you through one of them and leave the other one for you, right? But you can freely interchange the order of integration because it's a nice function. X minus y is nice, and Fubini's theorem lets you interchange nice things. But yeah, all these problems basically always come down to just figuring out how to parameterize one, or sorry, how to put the bounds of one x in terms of y or vice versa. So this is y in terms of x, right? So this will do really nicely for when you're integrating with respect to y first, because that just goes from whatever the smaller one is, which is x squared, right? Because on this domain, for this shape, x squared is the lower bound, whereas minus 2x is the higher bound, right? And that goes from what is this intersection point? I think I found it earlier, but you can find it for yourself. But it's like -2, 4, I think, right? You can figure out what that point is just by setting minus 2x equal to x squared and solving it. You get minus 2. So that goes from minus 2 to 0. So you can basically just go ahead and do this integral, and it shouldn't be too bad. I think this one's actually quite nice. But this other one sucks, because now instead of y being in terms of x, for this other one you need x in terms of y, which is basically x is equal to minus 1/2 y, and x is equal to the minus root of y. It has to be minus, right? Because look, every value of x here is negative, so it's clear that the positive root isn't the right one. So yeah, what happens here? Now we're sort of to write the bounds for this thing. You basically need to think, okay, well the left, as x goes from like left to right, the left is minus root y, and the right is like minus 1/2 y. And now y goes from 0 to 4, like 0 down here up to 4 up there. Okay, so you basically just got to integrate this crap, and it's terrible, a little terrible, but like, conceptually simple. Maybe I'll do it out quickly. But okay, so this becomes x squared minus yx, this is x squared of 2, from negative root y to 1 minus 1/2 y. And if you plug that in, I think what you get is, okay, and then integral dy from 0 to 4. And then that's equal to like 1/8 y squared plus 1/2 y squared. Plus like y over 2. This is right. No, so this is minus 2 plus y to the 5 halves. Or is it 3 halves? And now you got to integrate that from 0 to 4 dy. And at this point, it's just a bunch of crunching out a bunch of arithmetic, but I think that comes out right. Yeah, this is just 5/8 y squared, right? This is 5/8 y squared. Anyways, you crunch out the arithmetic and you end up with minus 52 over 15. I think this is just nasty computation and not testing anything interesting, but it is what it is. So I'll let you do the other integral, and this one shouldn't be as bad because there's no square root. But yeah, right. The point is when you're integrating with respect to x, you can treat y as a constant, and when you're integrating with and vice versa, right? Basically, the idea is, yeah, hopefully you're all familiar with what this notation means, right? This notation just means like plugging in the bounds of minus 1/2 y and minus root y to get rid of the x's. But anyways, the next part is basically asking you to find the average value over this domain. And what that means is just take this value over here and divide that by area of the domain. So the area of the domain is just this thing, right? And you can find, it's a little bit hard to see immediately, but hopefully it's not too bad, where you can just find the area of the triangle and subtract out the area under the parabola. Yeah, this is the parabola. So this is easy, right? This is just base times height over 2. This is 2, and this is like 4, I think. So the area here is equal to like 2 times 4 over 2 is equal to 4, I think. Whereas over here, you have to find it with calculus. Use single variable calculus, but that's not bad, right? That's just the integral from -2 to 0 of x squared. So just take this area and subtract out this area, and I think you'll find that it's going to be like the area I think I got was like 4/3. You know, like this thing minus the other, I think I got was like 4/3. And then I think you just divide 52 over 15 by 4/3, and you get what you get. So yeah, I think that's all there's to say at this point. Good luck with your finals, and yeah, hopefully it all turns out well.